Hello everybody, nice to meet you. We have today a very nice problem. We'll solve it together. Of function f of n is and it is equal to this is first simplification. Every integer can be written into in one of the three following forms, or I have three cases. First case is when n is square of an integer, and the second is when n is between k square plus 1 and k square plus k, and the second when n is between k square plus k plus 1 and k square plus k plus 2k. And we will give the expression of this term in each case individual. In the first case, we have square of n plus 1/2 is clearly equal to k, because we have n is a square and can get outside. And of course, for the second case, we have n located between k square plus 1 and k square plus k. Then n is less than k plus 1/2 k square minus plus or minus 1 and a 4. Then we have square of n is less than k. If we put square here, then it is smaller than the square of k plus 1/2 square. And this implies that square of n plus 1/2 is less than k plus 1/2 plus 1/2 is equal to k plus 1. This inequality is strict. And also this one. Because of this term, because we have n is smaller than this quantity minus 1/4, and when if we omit this quantity, then it is strictly smaller than k plus 1/2. And this implies that uh, integral part of t is equal to k. Now we'll do it for the third case. N is between k plus 1 and k squared plus 2k. And this implies that n is greater than this term, and this term is equal to k plus 1/2 plus 304, and this strictly greater than k plus. This implies that square of n is strictly greater than, and then square of n plus 1/2 is greater than k plus 1, and then and now we know when this quantity is equal to the first case, it is equal to n. First case, it is equal to n plus this n plus k, but k is exactly the floor, the integral part of square of n. In this second case, it is also equal to n is plus square of n. But in third case, it is equal to n plus square of n plus 1. Now let's pass to this theorem with the first assertion. This corresponds to the second case we have seen before. Just pose n equals k squared plus alpha, and this is between k squared plus 1 and k squared plus k, for we have alpha is between 1 and k minus 1. Alpha is an integer, positive integer. So we have seen before that plus 1/2 is equal to k. This is exactly, and the second assertion is exactly the third case. Just pose n equals k squared plus k plus alpha is less than k squared plus 2k because alpha is less than k, and k squared plus k plus 1 because alpha is greater than 1. And then we are in the third case we have seen before. This implies that square of n equals k plus 1. For the third assertion here, just suppose k prime equals k minus 1. Then the alpha here goes from 1 to k prime. And if we write n equal k prime square plus k prime plus alpha, then n is located between k prime square plus k prime plus 1, because alpha begins by 1, and k prime square plus k prime plus 2k prime. And in the third case we have seen before, we have equals k prime plus 1. Then it is equal to k minus 1 plus 1, and it is equal to k. And then f of n is equal to n plus n square of n plus 1/2. Then it is equal to n is exactly k prime square plus k prime plus alpha plus k prime plus 1, and it is equal to k prime plus 1 square plus alpha, because here k prime plus k prime into k prime plus 1, then it is equal to k square plus alpha. So f of n equals k square plus alpha. Now let's pass to the fourth assertion. In the fourth assertion, we have n cos n cos k square plus alpha, and we are in first case I've seen before, and we have f of n cos n plus square of n plus 1/2, and this is exactly n plus n square of n plus alpha, because it is equal to k. Then f of n cos, this is exactly what we have written here. Now we pass to the assertion 5. We'll first prove that f of n is never square, based on what we have seen before. We have seen that n can be t square plus alpha, with alpha between 0 and k, And in this case, we have f of n equals n plus square of n plus 1/2, and it is equals k square plus alpha. And we have seen this before. It is equal to k, and k square plus k plus alpha, it is strictly between k square and k plus 1 square, because this is less than k plus 1 square, because alpha is less than k. Then in the first case where f of the n gave no square. In the second case, n equals k square plus k plus alpha. Alpha goes from 1 to k. Then f of n is equal to n, and n is exactly k square plus k plus alpha plus and if n has this form, we have seen before that plus k plus 1, and this is equal to k plus 1 square plus alpha. And then f the n is strictly with k plus 1 square and k plus 2 square, because alpha is between 1 and k. And also in this case, f the n cannot be square. Now we come to the last step. If m is an integer, m is not a square. Then we have these cases. M has this form, or M has this form. Alpha goes from 1 to k minus 1 here. Or M has this form. These are the three possible forms if we suppose that n is not square. In the first case, and our objective is to find n such that f of n equals m. This is our objective. Our objective is to find n such that f of n equals m. In the first case, n equals k square, because we have f of k square equals k square plus k square plus square root of k square plus 1/2 and this is equal to I write here, is equal to k square plus k. In the second case, I will use this because I have m has this form. Then I take this as m. Then n equals k minus 1 square plus k minus 1 plus alpha, and f of n equals m. In the third and last case, I have m has this form, and I take n as then n equals k square plus alpha. Then the range of f is equal to n minus k square k equals 1, 2. There is a function f misses their squares. Goodbye.